So we'll start our next presentation. This time we're going into the formats and codecs area. With our first speech is about Matroska and low latency streaming by Steve Lum. Give a warm welcome, please.
Hello, so I'm Steve Lum. I created, not alone, the Matroska. So for those who don't know, you might know the format MKV. So that was the other name for the format, the actual name. So Matroska was created as an open format from the beginning for it. So it was developed mostly on the web with people who mostly never met each other. So mostly on IRC mailing list or the Doom9 forum. And it's mixing lots of technologies that were kind of emerging when it was created. So the idea was to replace AVI. There was OGG at the time, XML, Unicode, and Semantic Web, and we mixed all of this together to create the format. It was developed in a way that's inspired by what was done on the web, so everything was open, everything was royalty-free. And the original goal was to have a long-term storage format, something that would be usable for 10 years from when it was created in 2002. So in 2018 it is still used, so we reached that goal. And the other thing was to have low overhead, because since it's inspired by XML, it's very verbose, so we try to remove as much verbosity as possible. And also streaming friendly, because the design was always so it's the basis format for WebM, which was created by Google and Mozilla a few years ago. And so you'll know it's also used as MKV, and there's also MKA for files with only audio. There's also right now IETF working group to standardize Matroska. It's called CLAR, so it stands for Codec Encoding for Lossless Archiving and Real-Time Transmission. So the work group is working on EBML, which is the binary XML that Matroska is using. Matroska, which is now split in 3 different documents now. That might be all, but at the time each project had about 13 contributors, 300 commits, so mostly on documentation, cleaning the documentation that existed and improving it. The project, the work group started in 2015 and still ongoing, and still a bit of work to be done until we have final RFCs for Matroska. The work group is also working on the standardization of FFV1, which is a lossless video format, and also FLAC, which I'm sure you all know. So my talk today is talking about the latency in Matroska and how it can be used and how does it compare to other solutions. So first, to make sure we all talk about the same thing, the definition of latency I found on Wikipedia is latency is a time interval between the stimulation and response, or from a more general point of view, a time delay between the cause and the effect of some physical change in the system being observed. So basically here there's a diagram of what's happening when you actually do some, for example, live streaming of video and audio. So first you have, for video, you have frames which go into an encoder, then muxing, that means putting it in a format that can be, for example, mixed with audio or and also adding timestamps and stuff like that. Then it goes through the network. Then on the other side, there's the demuxing, so to get the uncoded frames that goes through the decoder, and then you get the frames. So each of these steps actually introduces a latency. I'm not going to talk about all kinds of latencies, for example, not the network, but some that are more involved in what Matroska does. So, for example, when you... Okay, that's supposed to be red. So the video encoding latency, for example, usually you have frames 1, 2, 3, 4, etc. that come from the camera. Then it goes through the video encoder, and usually when you have something pre-recorded, the codec can encode the frames in a different order than they are received to have better coding efficiency. But for live streaming, you don't want that. You don't want to have frames that appear very late compared to when they're supposed to do. So for live streaming, you actually have to put your encoder in a mode that always sends the pictures in the same order. So basically, live streaming is always a special case of encoding and muxing and everything. It's not the general case of how most people use video usually, but it's growing since most people now watch videos on YouTube or whatever, new Facebook. And that's increasingly going through the web and network, so that's becoming more and more important. So how does Matroska store information? So that's how, when you look at inside a Matroska file, you have first a very small header, the metastick, which actually tells you where these parts are. So when you read here, you can quickly go here if you want to. Then these parts are the actual audio and video that you're going to read. Here it's for seeking if you want to go quickly to a place. If you have that information, you can go here. Chapters, like it's regular chapters, and tags for all metadata to tag. Actually, you can tag this information, but also this information with tags from here. But in streaming, you actually don't have a lot of these parts. You only have the header and these parts. The metastick, since you're not going to seek during live streaming, is useless. And the cues, you're not going to seek back, so it's useless as well. You cannot introduce chapters for the same reason you're not going to seek in the file. The only one that could be used is tags that you would actually put before sending the actual data. So WebM is actually exactly the same as Matroska. It just have at the beginning it says WebM instead of Matroska. Otherwise, it's the same thing with some feature removed. So it's basically a Matroska profile. So in WebM live streaming, it would look exactly the same as in Matroska. But most people don't use actually live streaming this way. They actually use adaptive streaming. So when your connection is better, you can have better quality, or your connection is bad, you have a lower quality version. That's why when you do live streaming in Dash, which is one of the version of adaptive streaming, you actually have, for example, the audio can be split from the video, so you can have a better quality video with a lower quality audio. But the files actually looks the same. It's always still a header and a cluster for audio, and here it's still always a header and cluster for video. The only special thing is that the transition here, when you go to a better or lower quality of bandwidth, the boundaries here have to match always, and in all the versions of the same file with different qualities. So that's actually what most you are using when you're watching YouTube or Netflix. That's the kind of technology they use. But live streaming is even different. Because that's for even regular files that are already stored for a long time, but live streaming is actually has even more constraints. So Live streaming is basically when you have as little time between as we saw before, the definition of latency. It's as little time possible between the moment the frames are captured and the frames are received to the user. So you try to remove as much as possible stuff that you have. So basically, how does a Matroska file in live streaming? So basically a continuous stream of data coming. It's not a file you're reading, but a stream. So basically, this part is always there, and it's the same part. I don't know. Yeah. So it's this part that we had here. It's always the same structure. Then you have your audio and video. So I took an example of a file and from fragmented MP4, and I did it in Matroska to see the difference. So the header on Matroska was 460 bytes big, and then each cluster has a header. We're going to see that after, and then the data. The header is 25 bytes, and then you have the data. So the extra data is here, is that much data. And for fragmented MP4, you also have a header and then the data. The header was 2,100 bytes, and the equivalent of a cluster in fragmented MP4, the overhead is for 850 and the data. So you can already see Matroska is saving space. So that's in more detail what a cluster, where you actually save the frame. When I say frame, it can actually be video or audio. It's exactly the same thing. So in each cluster, you have one timecode for the cluster, and for each what's called block, you have a frame and a header. So each frame has a header that gives its timestamp and other stuff. So basically, before you start getting the first frame on a cluster, you have 25 bytes. And for fragmented MP4, the structure is a bit more complex. You have this atom, which consists of more atoms inside, which is like 1K, and then the actual data, where you have each frame. So you have to get all this data before you actually get this frame. So there's so here, what I call frame latency is how much time or how much data, it's kind of the same, do you need to actually get the end of the first frame that you can send to your decoder. So here, for a frame of 40K, you would have 40,025 bytes before you actually can send it to the decoder. For fragmented MP4, you actually have to have this 1 kilo and then 40,000. So again, the latency is better in Matroska. Again, that was a real live sample, and I just transformed into Matroska to see the difference, but it's the same. And the lower the bit rate, actually the bigger difference it makes to use Matroska. So basically here, the other thing you have is buffer latency, because as you can see in Matroska, you send one frame after the other with its header. In a fragmented MP4, it's different. The header for each frame is actually stored at the beginning. So in terms of latency, before you get this, you need to know all the frames you're going to have in that whole big block. That means before you actually get frame one, you need to have all the frames and wait. So as we see so earlier, so if you have blocks of 2 seconds in adaptive streaming, then that means you need to cache 2 seconds of data before you actually can send it, because before you can write this data, you need to know all that stuff. So that's, for example, in that case, 2-second latency, where in the case of Matroska, it would be just that amount of data, so 25 bytes, and then the amount of the frame. In this case, it was 20 milliseconds. And then, so we already see that Matroska has a big advantage here. The other format that's used a lot in streaming, and that's actually the format that was used in Apple's adapting streaming format. They insisted on using TS, so but now they've changed. They're using fragmented MP4 as well. So the same for one frame in Matroska. How does it work in transport stream? So one frame is actually cut in 184 bytes, and then each of these 184 bytes is encoded in 188 bytes. So each has a header, so 4 bytes header, then a part of the frame, then a header, a part of the frame, etc. So actually, to get the first frame, you actually have to get all the parts of the frame plus all the headers. In the case of the 40,000 kilobytes frame, the overhead, the extra data you have to download compared to the same, to get to the end of the same frame is 869 compared to the, so the 869 is the difference compared to the 25 bytes. So there's also less latency in Matroska than transport streaming. I'm early. So basically we saw the difference between Matroska and fragmented MP4. So the advantage of Matroska compared to this is a kind of smaller overhead from the network. There's actually only like 400 bytes difference between the two formats, so it's not that much. But for example, if you buffer 2 seconds in adaptive streaming, that's your latency that you're going to have in fragmented MP4. But in Matroska, you don't have data. You need to get to the end of the first frame is like 2 or 3% of data. So that's data you could actually use for better encoding in your codec. And the buffer latency, so the amount of data you need to get to the end of the first frame is the same compared to MP4, where you need to get the whole let's say 20 or 40 frames before you can actually start sending them. And that's actually early, so I hope you have a lot of questions. And I have some stickers in my bag, and you can also go on the Videoland booth in Building K. There's a Wheel of Fortune. You can win lots of stuff, and there's also some stickers there. And also, thank you.
Jérôme.
Hello.
Hello.
How are you?
Fine. I have a presentation just after you, so I am a bit stressed. But before that, I am curious about how you compute the cluster size before sending the second and third frame. How do you know the size of the clusters when you need to write this size in the bit stream?
So I'm going to go back to show. Let's say here.
Yes.
So as you said, so since it's inspired by XML, actually each element in EBML has an ID and the size of the data that it contains, and then the actual data. But in live streaming, there's a feature in Matroska and EBML actually that where you can actually tell this element contains data, but I don't know how much, so I'm not telling you the size, and you keep reading until you find the same cluster beginning, and then it's a different one. It's called, there's different ways to call it, but usually we call it unknown length. And so you just send that in your stream, even though you don't know the size, you don't need to wait until you know it, you just send it, and too bad. And on the other side, the parser knows it has to handle that size.
In that case, how do you know at which level of the Matroska you are, at the block level or at the cluster level? It is with the key of Matroska, it is a cluster, so it is this level?
So that's how EBML works. So to read an element, the ID, you have to actually know what the parent is, and then its parent, etc. So when you find data that are not for this parent, you look in the other parent, is it for this parent, etc. And then you actually find that where it belongs.
Okay, thank you.
Another question? Oh, that's okay. I start here, and I have two in front.
So MPEG-2 transport streams are able to be cut off at the 188-byte boundary, which means that if you've, for contribution sources happening before what is distributed, you're able to, when you have multiple, say, streams for resiliency going into your final encode, you can just mix and match if you've got network problems or other kinds of, say, encoder issues. Are you able or not able to do that with Matroska in a similar way, given the format?
No.
Okay. So I had two questions. Want to start?
Okay, so about live streaming, have there been thoughts about program metadata yet?
What do you mean program metadata?
Such as EPG and things like that.
Well, in the case of adaptive streaming, usually the metadata are not in the stream. It's it can be in the manifest. So, so in adaptive streaming, a manifest is actually an external file which describes where to find these files. For example, with a general rule, they're not rewriting the file every time a new segment comes. And they can put all kinds of data in there. It's not related to the actual data.
Yes, but in case of a single stream, live stream.
So yeah, like this, like I said earlier, no, you could actually put these tags. So tags, you can, like the author or the date it was produced, or you can put all kinds of stuff. You could actually put it here. And because it's a live stream, you could actually put here, and you can add a new one during the streaming to actually change the data. Well, like if you play a song and then the song changes, then you have new metadata that you can introduce in the middle. It actually exists for MP3 streaming, and you get ID3, or I don't remember the format, in the middle of the stream that you have to parse, and then you get the new song that's playing. It could be also done the same way with Matroska.
Okay, thank you.
I feel that you are mixing explanation on file format and what you put on the wire for doing the streaming. And you are comparing fragmented MPEG-4, which is a file format, with the streaming, which is maybe HLS or Dash, whatever. And why don't you compare to the other ways people are doing low latency streaming, like RTP or MGPEG, which are the low latency solution nowadays? Well, since ever.
Okay. Compared to RTP, RTP is a network thing. And usually they actually, well, there's all kinds of formats for RTP, but usually there's not even a container. Well, that would be a Matroska in this case. And what I'm talking about here is actually either files for adaptive streaming, but that file you can still write on the server while people read it, which cannot be done in fragmented MP4. That's why it's mixed between file format and streaming format, because in the case of Matroska, it can be both. In the case of fragmented MP4, it cannot. But compared to RTP, I mean, it's not the same goal. You can probably, and you do get better latency with RTP, but then you don't scale that well, or you have other issues, and that's why people on the web, at least, they're not using that because that's not how their technology works. But for example, RTP is used, for example, if you have Twitch or other stuff, I think Twitter Live, the client is actually sending to their server in RTP format. But then for distribution, that's not a good format for them. They need something else.
Thank you, Steve.
You're welcome.